Now that we have a pretty good idea that on any cutting plane, just for an axially loaded bar, we can have a normal and a shear stress, what happens when we have a general solid? And we're going to identify that by calling this mini topic the general state of stress. And let's go back to our original solid. We've got a solid in equilibrium that looks something like this, and we have a point P. And if somebody is to say to us, what is the state of stress at P? So that would be the question that's posed to us. And we'll put that in quotes. What is the state of stress at P? What do they mean? What does that mean as a student of solid mechanics? I am one, you are one. What does it mean to us when they ask what is the state of stress at some particular location? When we first introduced this topic, we made an arbitrary cutting plane. We just sliced it through. But what happens if this is a component that's made by Westinghouse or General Electric or some other company that maybe is not bankrupt? But we've got a general state, and what does it mean when we do that? Well, typically we would start then by identifying a coordinate system. So I would put this in three-dimensional space. So let's call that X, then Y, then Z. It's not really important what those orientations are going to be, but we do have a rectangular Cartesian coordinate system. And the first thing that we do, so we'll bullet this, so let's make 2 bullets. The first thing that we do is we make a cut perpendicular to the x-axis. So we are going to cut it perpendicular to the x-axis. So let me try to kind of redraw what I've drawn up here. That means we're going to slice it like this. So I cut it this way, and we are going to look then at what the state of stress is going to be then on that resulting cut. Now I want to point out that as we do this, we can separate this particular solid. We split it apart. So let me try to do that. And I've got one going like this, and then I've got another one that's going like this. So I've made, if I cut and separate, I'll say cut and split, just because it's less letters. Cut and split. Then what's happened is now we have 2 cut faces, but they were made by the same cut. Now this one, notice, that's going in the plus x direction. So we are going to call, this is all right, this is plus x. This one we will call the plus x face, because the unit normal vector to that face is going in the positive x direction. This one, on the other hand, is going to the left. So that I would call the minus or negative x face. So when we make a cut like that, we get 2 particular cut faces, and that's going to be important. And by the way, they're both containing P. So P is there and there and there. Now what happens is we're just going to focus on this one for right now. And so I'm going to draw it like this. So there is our cut face. And now what happens is that we are going to now split that resultant force that we had earlier. But instead of splitting it into 2, we actually are going to split it into 3. So I'm not going to draw the original force that we had. Instead, I'm going to go and break it down. Here's the first one. That's the one that is going to be in the normal direction. So that's the one that would come from taking the limit of n divided by the delta n divided by the delta a. But now we're going to take the one that is parallel to the face. So remember, we had a second one originally. But now what I'm going to do is I'm going to split it into its 2 components in the plane. So that would look like this and like this. So in other words, this is going to be my sigma. But the 2 that I had originally that were parallel to the face, I'm going to split. So I'm going to have one value of tau there and another value of tau there. So another way of looking at this is if let's take another cut face like this, and I have a force that's going off this way. around my little delta A. Remember what we did. We split it into the one going this way and then the one going this way. So what we've done is we split the tangential component into the two that go in the y, z faces. So one is going in the x, one's going in the y and z. And then we do the following. I say that this normal stress is going to be on the x face in the x direction. The shear stress component, I'm going to say, is on the x face, and that's going to be in the y direction. This one is going to be on the x face in the z direction. So what we do is we give both our normal and our shear stresses two subscripts. The first one is the face on which it acts. The second is the direction. Now notice the XX, if it's a face and a direction and they're the same, it is by definition a normal stress. The other two, if it has a face and a direction that are not the same, it is by definition a shear. So if they're going, if these two guys, if they are the same, it has to be a normal stress. If they are different, then it has to be a shear. So that's an easy way to remember what the character of those things is going to look like. Now, if we have something like this, then we also, because of Newton's third law of equal and opposite force resultant, we have to have the equal and opposite on the other part of that particular solid. Now, I'm going to only focus on the normal value right here. If I take a look at this blob, like so, and if I have a sigma xx going this way, then what that means is on the opposite side, there had to be a force that was equal and opposite. So I would get that particular value. And this sigma xx is what I would get when I took the result of the total resultant force divided by the area. But I would also get the same thing like so. Now notice they're both pulling outside, or they're pulling out on the cut face. So those two parameters would both be tension. They would both be T or positive normal stresses. So we get the same value and the same sign on the plus x face and the minus x face. It would still be considered to be tension if it were going in that particular direction. So whenever we make a cut, we have two values that are exactly the same. We have sigma xx on that face, we have sigma xx on this face. But now we do something that's going to look a little bit strange. We're going to switch position. I'm going to bring this one over here. I'm going to put it behind. And so I'm going to draw a little diagram that looks like this. This is the plus x face, so there is my sigma xx. Let me put a single underline. That's the face that I'm talking about. So this face right here is this face right here. Then I'm taking the one that is behind, that's this one right here, and I've moved it. Now that's going to be that back or negative x face. And we still have the exact same value. So that's going to be sigma xx. Now, this is odd or a little bit peculiar because we're really looking at a point. In other words, the state of stress on this face is exactly the same as this face. It's the same location in space. All we've done is kind of move one of those faces so that we can draw it a little bit easier. And this is what we do in mechanics. We move the face a little bit and draw the same value just so we can visualize it a little bit better. So this is strictly to visualize because it tells us that when we talk about a positive sigma xx face, it can either be on this cut or this cut, and it's going to have the same value. So if it's, for example, 10 ksi, I have 10 ksi tension going like this, 10 ksi tension going like this. Even though they're going in the opposite directions, they are still considered to be tension. Now we can use that we can use that fact that we are going to split these solids and then move the faces. And that is going to help us to identify what the nature of the stresses would be. So typically we show this on a little cube. I'll say we show on a small cube or a parallelepiped. And we draw it like this. So I'm going to draw it in dashed lines like this, this, and this. Now earlier I put the x going to the right, but I'm going to move this. I'm going to say that's x, that's going to be y, that's going to be z. And now what I want to do is draw a little element that looks like this. Like so. So there is our little, that really doesn't look like a cube, that is a parallelepiped. So on the x face, we draw the following. I'm going to draw this one. That's sigma on the plus x face in the plus x direction. Then I also have this, and that's going to be tau. That's the shear stress that's on the plus x face in the plus y direction. And then I have the one here, and that's going to be the shear stress on the plus x face in the plus z direction. So on the front x face, I have 3. There are going to be one value of sigma, there's one normal stress, and there are 2 values of tau. Now on the back face, because of what we just talked about, because of Newton's third law, we have sigma xx, same value. We have tau xy, but now it's going to be going down like this. So that's my tau xy. And then the tau xz is actually going the opposite direction. So that would be my tau x face in the z direction. So the front x face and the back x face all have 3. So we'll say same for the back x face. There are 3 components on each one. And that's a good time for us then to stop the third part of our lecture for today.